Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 3.2, which is sort of a follow-up to the definition of the determinant. In section 3.2, we're going to learn some properties of the determinant, and through those properties, we're going to learn two major things. One is that through these properties, we'll learn sort of some better ways of calculating the determinant rather than relying on that sort of complex definition involving the permutations and inversions and all of that. And two, we'll see that once we've sort of set up a couple of these properties, we'll be able to formally establish the relationship between the determinant and invertibility. So, a couple major things in this. First of all, though, we're going to establish a sort of result that we hinted at in the sort of previous video, which was about the determinant for upper triangular, lower triangular, and diagonal matrices. So, in the last video, one of the examples was, I believe, an upper triangular matrix, and we saw that once we went through that sort of long-winded using the definition of the determinant, we found that the determinant, despite going through and calculating 24 different things, turned out just to be the product of the diagonal elements. This turns out to be the case whenever a matrix is upper triangular, lower triangular, or diagonal. So let's go ahead and state this. So let A be an n by n upper triangular, lower triangular, or diagonal matrix. Then, if that is the case, the determinant of A is simply A11 times A22 times dot 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 ANN. In other words, if you have a matrix that is upper triangular, lower triangular, or diagonal, the determinant is simply the product of the diagonal elements here. Now, in your textbook, they go through and they do a proof for when it is upper triangular. We are going to go ahead in this video and prove it for when it is lower triangular. You don't really need to worry too much about that diagonal case, because if you remember, the definition of a diagonal is something that is both upper triangular and lower triangular. So if you've proven one of these, well, then you automatically have this guy for free. So you can look at your textbook for the proof when it is upper triangular. We will do the proof for when it is lower triangular. So let's do our proof here. Let's let A be lower triangular. And again, upper triangular is in textbook. Okay. So let's remember what that means, right? For something to be lower triangular. So A is lower triangular implies that Aij, well, remember, being lower triangular means that your non-zero elements, if they exist, have to be at the diagonal or below, which means that anything where the column position is larger than the row position must be 0. So Aij equals 0 when I less than j. Does this mean that things are not 0 when I is greater than or equal to j? Not necessarily, right? Those could be 0 as well, but just remember that to be lower triangular, you must be 0 when your column position is larger than your row position. All right, now let's go ahead and consider the determinant here. So consider determinant A. Let's use the definition of the determinant. It is the sum over those n factorial different permutations, right? Where you take the sign of each permutation and then multiply it with the product, where you do A1P1 down to ANPN. Okay, so the determinant, remember, is a giant sum of a bunch of products. Now, we're going to use the fact that we know that since A is lower triangular, there are a bunch of zeros. And remember, if something is 0, then this product is also 0. So keep in mind, A1P1 dot 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 ANPN, that product equals 0 if any AKPK equals 0, right? Since this is a product, this whole product is 0 if any one of those single elements is 0. So let's consider the ones that might not be 0. So let's consider the conditions for this product to be potentially non-zero. Okay, so let's think about what conditions have to hold for this product to potentially be non-zero. In other words, to potentially contribute something meaningful to the determinant. Well, let's go ahead and start by thinking about this A1P1. So let's think about what that sort of needs to be, right? So A1, P1 is potentially non-zero when, well, remember, we know it is automatically zero if the column position is larger than the row position. Since the row position is 1 here, that means this guy is potentially non-zero when, well, if we can get rid of when and say if pi equals 1. If pi is anything else, if pi is 2, 3, anything larger, then this guy is guaranteed to be 0, right? That's what we're sort of saying there, right? Is that if this P1 is anything larger than 1, then the column position will be larger than the row, and this guy will be automatically 0. So the only way that this guy is potentially non-zero is if P1 equals 1. All right, let's consider A2, P2 is potentially non-zero if, well, if we think about that, A2, P2 is going to be potentially non-zero as long as that P2 is not larger than 2. So that means that P2 equals 1 or 2. And of course, this would continue on. A3, P3 is potentially non-zero if P3 is 1, 2, or 3. If it's anything larger than 3, then this is guaranteed to be 0 by this. And of course, this would continue on. AN, PN is potentially non-zero if Pn equals 1, 2, 3, down to n. Okay, but let's think about these restrictions. Remember, these P1 through Pn's have to be distinct. So once a value is selected, it can't be used for any other one. So we just saw up here that P1 has to be 1 for things to be potentially non-zero. So if P1 has to be 1, then P2 can't be 1. So P2 has to be 2. Well, if P1 is 1 and P2 is 2, then P3 can't be 1, it can't be 2, it has to be 3. And this process would continue all the way down where everything would be eliminated and Pn would be n. So what this is basically saying is that A1, P1, AN, PN is only potentially non-zero if P1 equals 1, P2 equals 2, Pn equals n. Otherwise, this product, right, anything else, will automatically be 0 because at least one of these elements will be 0 by the fact that it is lower triangular. So we know that the only potentially non-zero product is this one where P1 equals 1, P2 equals 2, Pn equals n. All right, we'll need another sort of page here, so let's go ahead and add one more page. So let's think about what this tells us. So this tells us that the determinant of A, which we know is that giant sum, the sum over these n permutations, P1 down to Pn, A1, P1, AN, Pn. Well, this whole sum is meaningless because n factorial permutations. Let's just make that a little cleaner looking. N factorial permutations. Well, this whole sort of sum is sort of meaningless because we just found out there's only one product that is potentially non-zero. So we can actually simplify this to determinant of A is the sign. Remember, the only permutation we care about is where P1 is 1, P2 is 2, etc. So 1, 2, n, and then A11, A22, ANN, because the only one that we were interested in is where P1 through Pn equals 1 through n. Well, what's the sign of that permutation? Well, this is the natural permutation, no inversions. So this would be -1 to the 0. So determinant A is -1 to the 0, A11, A22, ANN. And determinant of A would then be A11, A22, ANN. And that's exactly what we wanted to show. Okay, now that is the proof that shows you guys that if something is lower triangular, then it has its determinant is just the product of its diagonal elements. If you want to read through the textbook, you can see how to do this for upper triangular. The only difference for upper triangular is that you actually start with a restriction on Pn. Pn is guaranteed to be n, and then you work down to P1 needing to be 1. So you sort of do this in a reverse direction. Otherwise, the proof is very similar. For diagonal, you could go through and do this whole thing over again, or you could simply say that a diagonal matrix is upper triangular / lower triangular, so you automatically know that it also has this property. So that's the sort of important theorem on how we calculate determinants very quickly for upper triangular, lower triangular, and diagonal. All right, so why is it so important to know this property? Well, if you tie this sort of back into things that we were doing earlier, we learned a process to take a matrix and put it into upper triangular form. Specifically, we learned how to put it into row echelon form. So what this is sort of saying is that if you can manipulate your matrix into upper triangular form, you can very quickly calculate its determinant. The last sort of remaining question then is, what happens when you do those elementary row operations? Do they impact your determinant? And the answer is they can, depending on which operations you do. So we're going to now study the relationship between the determinant and elementary row operations. So let's go ahead and talk about that. Elementary row operations and determinants. So we have 3 sort of elementary row operations, and what we want to do is discuss what each of these elementary row operations does to the determinant. So let's talk about this. Is sometimes called property 1 of the determinant. So let's let B be constructed from A by interchanging 2 rows. Okay, your first elementary row operation you learned is interchanging 2 rows. So let's let matrix B be constructed from matrix A by interchanging 2 rows. Then this causes the determinant of B to be negative the determinant of A. So if you interchange 2 rows, then that changes the sign of the determinant. Property 2 is let's let B be constructed from A by multiplying a row by non-zero scalar k. Okay. So this is your second type of elementary row operation where you multiply a row by a non-zero scalar. Then the determinant of B is k times the determinant of A. So if you multiply a row by a non-zero scalar, then you also multiply the determinant by that non-zero scalar. Now, we're going to, before we get to the third elementary row operation, let's do a quick follow-up on P2 here. So up on P2. If A is n by n and B equals Ka, then, okay, so this is basically saying if you've got an n by n matrix and B isn't just a single row multiplied by a non-zero scalar, but B is the entire matrix multiplied by that non-zero scalar, then this determinant property will happen n times because there's n different rows. So then the determinant of B is actually k to the n determinant of A. So what this is basically saying is if you multiply a single row by a scalar, then you multiply the determinant by one factor of that scalar. If you can multiply every row, so the entire matrix, by a scalar, well, then you would do this operation n times, and so you get k to the n times the original determinant. All right, we had one more sort of elementary row operation here, so we'll call this P3 of the determinant. So let's let B be constructed from A by adding a non-zero scalar multiple of one row to another row. Okay. Then the determinant of B is actually equal to the determinant of A. So if you use that sort of third elementary row operation where you add a non-zero scalar multiple of one row to a different row, then that actually does not impact the determinant. So this basically tells you guys that if you use those different elementary row operations, each of them can kind of impact the determinant in their own way. Interchanging two rows negates the determinant. Multiplying a row by a non-zero scalar multiplies the determinant by that scalar. And adding a non-zero scalar multiple of one row to another row doesn't change the determinant at all. So what this should give you as sort of a little follow-up to these three, follow-up to P1, P3. If A is row equivalent to B, so if A and B are two row equivalent matrices, then determinant of A is equal to K, let's use a different constant since we use K up there, is equal to, let's call it big C, determinant of B for some non-zero scalar C. In other words, what this is saying is if you have two row equivalent matrices, then the determinant of one of them is some multiple of the determinant of the other. Because if you think about these operations, each of these operations either does nothing, simply negates, or multiplies by a non-zero scalar. So if you do a bunch of those operations, all those scalars mix together for some other general non-zero scalar. Okay, so these three operations basically tell us that if we use elementary row operations to put a matrix into upper triangular form, then from the first theorem, we know we can calculate the determinant of that upper triangular matrix very quickly, and then we can use this information to track down the original determinant. We will see an example of that in just a little bit, but we'd like to first go ahead and prove these two properties here. We're going to prove this property a little bit later on because it turns out that it's easier to prove that one once we've established some other properties, but we will begin by taking a look at the proof of these two. And this is where we will continue to use and get more familiar with that straight definition of the determinant. So we're going to prove these two properties and then look at using these to do a more computationally efficient version of calculating the determinant. All right, so we're going to do the proofs of P1 and P2. So let's do our proof of P1. So what are we trying to show in P1? Well, we're going to let B be constructed from A by interchanging, let's call it rows R and T. Okay. We need to show that the determinant of B is equal to negative the determinant of A. So the only thing we're doing here is we're just specifying that the two rows we're interchanging are named row R and row T. So let's talk about the elements of B then, because most of the elements of B just match the elements of A. So Bij, well, let's think about that. Most of them are just Aij if I is not equal to R or T. If you're not in one of those two rows where we interchange things, then the elements of B are just the elements of A. If you do happen to be in row R, then you actually use row T of A. So we would say that Brj is actually Atj because we're interchanging rows R and T. And if I is equal to T, then we get Arj. So in other words, all this is sort of fancily sort of saying is that the rth row of B is the tth row of A, and the tth row of B is the rth row of A, right? So that's sort of a almost pirate sounding definition of what we're talking about in these elements here. Okay, so let's actually try to do our need to show then. We'll start from the determinant of B, use the definition, and try to build to the negative determinant of A. So what do we know about determinant of B? Well, we know it's the sum over the n factorial permutations, where we take the sign of each permutation. Now, normally we do P1 through Pn, but we sort of know that R and T are important moments, so let's go ahead and just write those out too. PR down to PT down to Pn, and then we'd have A1 P1 down to ARP. Oh, my bad, those should be B's there. Let's give ourselves a little bit more space to do this too. I'll try to write a little smaller. P1 down to PR, down to P2, down to Pn, and then B1 P1 down to BR PR, down to BT PT, down to BN Pn. So that is the definition of the determinant of that matrix B there. Okay, so what can we do with this here? Well, the first thing we could probably do is we would like to actually start phrasing this in terms of A. So let's use this definition here to rewrite these pieces in terms of A. So this tells us that the determinant of B is this summation over the n factorial different permutations. We're not going to replace anything in here just yet. So this is still P1 to PR to PT to PN. A1, P1, well, 1 is sort of being assumed that it's not R or T, so this is just going to be A1, P1. Then down here, BR, PR, well, that is where I equals R, so that's actually AT. So AT, PT. Oh, excuse me, AT, PR, because we're not changing anything about the column. AT, PR. Then this guy here, well, because that's the tth row of B, it's actually the rth row of A. So that would be ARPT. And then it looks like that would be ANPN. Why is that guy still just AN? Because again, we're assuming sort of row N there is not one of these ones that have been interchanged. So these guys don't change at all. They just go from B to A. These guys have those row positions sort of transposed there. Okay, so let's go ahead and see what we can sort of do with this. Well, what I sort of want to note is that we can still move these guys around, right? This guy sort of has a later row position than this, and that's sort of out of order from the normal definition of the determinant. So let's just change the position of these two. Now, all these things are multiplied, and of course multiplication is commutative, so it won't make any impact if we decide to reverse these positions. So let's go ahead and do that. So we have the determinant of B then is the summation over those n factorial different permutations. We still have the sign of each permutation. And then we have A1, P1. Now we're going to go ARPT, ATPR, and then ANPN. So all we're doing there is we're changing the location of these two multiplications. Now, what we should notice here is that this is almost the definition of the determinant of A, right? It goes A1, P1, The only problem is that we've got this sort of ARPT, but this PT doesn't match that PR, and this PR doesn't match that PT. So what we now need to do is we need to change these two so that this matches what we have here. Now, when we change two things in a permutation, we saw in the last video that that negates the sign of that permutation. So let's go ahead and do that. So this would tell us the determinant of B is the summation over those n factorial different permutations. And we're going to change the order of this permutation by swapping these two. So this would be P1, PT, PR, PN. And when we do that, we have to put a negative sign in front because we swapped two elements in the permutation. And we proved in the last video that negates the sign. Then we have A1, P1, ARPT, ATPR, ANPN. Now notice that each of these matches up with the column position here, and this goes A1 down to R, down to T, down to N, as it normally does. So this right here is the normal definition of the determinant. So we'll factor this negative outside the sum, which is certainly allowed. So determinant of B is negative the sum over the n factorial different permutations. The sign of each permutation, A1, P1 down to ARPT, down to ATPR, down to ANPN. And then, of course, this, like we just said, is the determinant of A. So we get that the determinant of B is negative the determinant of A here. And that's exactly what we wanted to show. So a little bit messy because of the fact that we had to sort of keep track of the fact that the two rows were interchanged and make use of this sort of T and R notation. But overall, not too bad. Use the definition of the determinant to show this property here. Property 2 will be much faster. So let's go ahead and do that guy as well. So proof of P2. So P2 says let B be constructed from A by multiplying row R by non-zero scalar K. Okay, what we need to show is we need to show that the determinant of B is K times the determinant of A. So let's do the same thing and talk about the elements of B based on the fact that we're only multiplying row R by non-zero scalar K. So Bij is Aij if I does not equal R, and is K Arj if I equals R. So in other words, all the elements of B are the same as the elements of A, unless you happen to be in that rth row, in which case you multiply by that scalar K. All right, let's do the same approach. Let's write out the definition of the determinant of B. It is the sum over those n factorial different permutations, the sign of each permutation. Of course, this time we should probably keep in mind that PR is going to be important, down to Pn, and then A1, P1 down to, B, of course, my bad. B1, P1 down to BR, PR down to BN, PN. Okay, all these except for this guy are just going to be replaced by A's, and this guy just needs to be replaced by K times the A values. So determinant of B is the sum over the n factorial different permutations, the sign of each permutation. This guy, like we said, that's not the row that we multiplied, so those are just A1, P1. This guy then is the one we multiplied, so we replace that with K, so KRP. Sorry, we should have our A there, KARPR. And let's put some parentheses around that, and then dot, dot, dot. And then finally, this guy should be replaced with ANPN. So there we go. The only one that sort of is replaced by something a little different is this guy being replaced with KARPR. So now what we can sort of see is that this K, well, since this is multiplication, he could be put right there. But of course, if he could be put right there, he could also be put right there, or he could be put outside the summation. So we can do this as the determinant of B is K times the summation of the n factorial different permutations. Well, we've got that. A1, P1, then down to ARPR, then down to ANPN. This, of course, then is the definition, right? Each of these matches the column positions there. These are in ascending sort of row order. So this is exactly the definition of the determinant of A. So we get determinant of B is K determinant of A. And that's exactly what we wanted to show. So that proves both properties 1 and 2. We'll prove property 3 later on once we've established some other properties of the determinant. Okay, so now going back, I know that was sort of two sort of lengthier sort of proofs there. So let's just remind ourselves. We sort of know that we've got these 3 row operations. Interchanging causes the determinant to be negated. Multiplying by a non-zero scalar causes the determinant to be multiplied by that scalar. And adding a non-zero scalar multiple of one row to another row doesn't change the determinant. This tells us that a quick way of calculating the determinant is to take a matrix, use elementary row operations to put it into upper triangular or lower triangular form, and then use the first theorem to quickly calculate the determinant. So let's see an example of doing that. So for this example, let's go ahead and let A, I think we want to do this guy. Let's let A be the matrix 3, 6, 0, 3, 1, 5, 0, 3, 2, 4, 2, 1, 3, 6, 0, 7. So it's a 4x4 square matrix. Let's try to calculate the determinant of A. So, of course, we could go through the process we learned in the previous video, write down the 24 different permutations, right? Because it's a 4x4 matrix, so 4 factorial is 24. And then calculate all those products, sum all that up along with the appropriate signs and see what we get. But we're going to try to do this a little bit faster using the elementary row operations. So let's go ahead and use a little bit of good notation here. Let's start by just writing this in sort of bars here. So 3, 6, 0, 1503, 2421, 3607. Okay, so now what we want to sort of do, remember this notation just means that we're trying to calculate the determinant here. Well, we can do several things, right? We're trying to put this in upper triangular form. So we'd like to sort of maybe have a nice pivot here to clear out the stuff down here. So you could interchange this guy with this guy if you wanted to, or you could recognize that this guy, if you divide everything by 3, will be a nice, easy sort of pivot position here. So I'll go ahead and do that. So let's first modify by doing 1/3 of row 1. Now, let's also sort of keep track, because we know some of these operations are going to change the determinant. Let's just keep track that this guy has the determinant we want, determinant of A. Okay, so let's use that elementary row operation. We get 1, 2, 0, 1, and then the other guys aren't going to change. Okay, what does this operation do to the determinant? Well, this matrix, now this guy here, does not have the same determinant as the one we actually want. Instead, it has 1/3 the determinant of A. But of course, if we could figure out the determinant of this, then we know 1/3 the determinant we want equals that. If we multiply both sides by 3, we'll be all good. So we're just going to make sure that as we do this, we keep track of how we've modified the determinant. Okay, now we've got this nice pivot position, so we can clear out the things below it. So let's do those operations there. Let's replace row 2 with row 2 minus row 1. Let's replace row 3 with row 3 minus 2 row 1. And let's replace row 4 with row 4 minus 3 row 1. Okay. So if we do that, the top row shouldn't change, 1, 2, 0. Then the next one, well, we should get a 0, then a 3, then a 0, then a 2. Then the next one, we should get a 0, 0, 2, and then 1 minus 2, so that's -1. And then the final one, 0, 0, 0, and then 7 minus 3, so it looks like 4. So there we go. Now, do any of those operations sort of impact the determinant? Well, that's property 3. Those do not. So this guy also has 1/3 the determinant of A. Now, this matrix right here is upper triangular. So we can take this guy here, 1, 2, 0, 1, 0, 3, 0, 2, 0, 0, 2 minus 1, and 0, 0, 0, 4, and we can just calculate that directly. That's going to be 1 times 3 times 2 times 4, which looks like that's going to be 3, 6, and then 24. So is that our determinant? Well, no, right? Because our determinant, right, is this guy back here, and this has 1/3 of our determinant. So we can say 1/3 determinant of A equals 24. So determinant of A equals 72. So we've gotten our determinant right there. Okay. So what this sort of tells you guys is, notice that this was much faster. Even though it was still a little computational, it's much faster than using the straight definition of the determinant. All you need to do, though, is be very careful about any operation, like multiplying by a scalar, that'll change the determinant. If you keep track of that, though, and then undo it at the end, you can use this to quickly get the determinant of this matrix. If you want on your own, you can use the definition and actually confirm that if you use the straight definition of the determinant, you will arrive at the same spot here. In the next video, we'll establish an important theorem that we sort of mentioned at the beginning of this one, that the determinant and invertibility are directly related, and then look at a couple more examples of that.